So I put grades in for the college trig final, along with any partial credit that I added in there. So I put it in the grade book out of 13, so it's not going to make a big difference either way. It's just about getting it done and making sure that we've got some proof that the things happen. So we've taken care of all of our See You Succeed responsibilities, which is nice. And like I might have mentioned, I forget if it was to you guys or to Fourth, the grade that you get in calculus is the grade that I send to CU for your college trig stuff. I don't just pick out all the trig and focus on that because that would be bad if we did that. So if you're worried about your college GPA, don't be, as long as your calculus stuff is good. Because that's our main focus. So I want to give you the credit for that instead. And this is the last year for See You Succeed anyway, so what are you going to do? What are you going to do, fire me? Yeah, right. I don't think so. Let me ask you, how is this implicit stuff going? Do you need like just a couple this morning just to kind of get the juices going, make sure you got it down? Or, oh, I see, yes, yes, yes. Okay, then yes, 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 it is. Let's turn to, I don't know, there's a couple of good choices. What's up, Maj? Oh, Feliz Cinco de Mayo.
That's for a play, but yeah, Cinco de Mayo. That's right.
Today's my mom's birthday, actually. Yeah, she is 74. 74 years young, still kicking it. All right. So the thing about what we've got left is there's not a ton of options. So I say we start on 253 with number 5. Okay. Because this one's not too bad because there's no product anywhere. It's just a bunch of individual DDXs that you're going to take along the way. And then once we do that, we'll set it equal to 0 because they want a horizontal tangent. So see if you can do that. See if you can find the derivative. Can you find dy dx by taking ddx of both sides? Let's see if we can all get to the same spot. And because they want a horizontal tangent, we'll see if we can figure out a way to make it 0. I haven't done this one yet, so we'll see how it plays out. But I do want to start. The next thing I want to start related rates today so we can practice it tomorrow so that when I'm gone on Friday, you've got some background that you can just kind of run. And obviously today, no homeroom. We're back to our regularly scheduled programming here on Wednesday. But Friday is still late start Friday, so classes will be short. So go ahead, give it a shot. See if you can find ddx of number 5 on 253. And we'll see what we can do with it once we get there. Maximize my space here. I'm just going to start right there. I'm just going to say ddx of remember, just treat it like you normally would. Do whatever derivative rule you need to. If the variables match, then you're good. If you're taking the derivative of x with respect to x, nothing extra we have to add. But if you're taking the derivative of something with y, just attach a little dy dx at the end. And if you want to make sure that your first step is right, check it against what's up there in blue. I don't need the plus 0 necessarily on the left, but just so you see what I did there with each one. You get to there, all right, you're off to a good start. Now just isolate dy dx. We got more than one of them, so we'll keep those on the left. We'll move everything else to the right. factor it out, divide it away. Now, if all they were asking us to do was to find dy dx, we'd be done right there. I saw 2 in common everywhere. And I don't know that you have to show, like, if you're okay, if you're comfortable with it, you don't have to show me that you factored it out in order to divide it away. You can divide it away. You can simplify. You just want to make sure that you do it everywhere. Nice. How did you do? Get that derivative? Get that dy dx? Good. Then you're off to a good start. Now, what we want to do is we can challenge ourselves a little bit. Let's see how it plays out. Honestly, I haven't done this one, so I'm not sure how it's going to work. But we want to figure out where this graph, which is definitely not a function that's got x squared and y squared, if it was just x squared and y squared, or 4x squared and 4y squared, if the coefficients were the same with addition in between, it'd be a circle. But because the coefficients are different for x squared and y squared, it squishes it out. Okay, so that's actually an ellipse. Right? Different coefficients there. And the whole minus 8x plus 4y plus 4 thing, all that does is doing the shifting. Okay, that's just kind of moving the center of that ellipse, or really kind of moving each of the foci to 2 different spots. But we want to figure out where this thing has a horizontal tangent. We want to find like the top of the ellipse and the bottom, basically, if that's what we can figure out. How do you think we can do that without actually graphing that? Yeah.
Solve for x.
What do you mean solve for x? What are we going to, like, what equation are we solving?
You set the derivative
Equal to 0. Okay, that sounds good. Let's take this derivative. And because we want this to have this graph, whatever it is, to have a horizontal tangent, what we want to do is set the derivative equal to 0 and figure out a way to get it. Can we find a way where this graph is going to be equal to 0 for its derivative? Well, it's a fraction. We've got this fraction. We've got x on top, y on bottom. It's okay. If I want a fraction to be equal to 0, what are the things I need to have true? What makes a fraction exactly 0? Yeah?
0 on the denominator.
0 on the denominator would make it undefined.
So 0.
Yeah, 0 in the numerator. Perfect. We want the top to be 0 and just the bottom not to be. Really, that's the focus. And so really, like, my next kind of step is really not like an algebraic move, but it's more of a critical thinking step that says reality setting in here. All I really care about is that the top is 0. And then I'll just make sure that whatever I get, that I'm not putting something into the bottom that's also going to make it 0. And we can solve this one pretty quickly. Right, slide the 4 over, divide by -4, and there we go. So I know for sure that whenever this graph stops at x equals 1, wherever that is, we'll have a horizontal tangent. But again, remember what this picture looks like. Right? It probably, based on what we've got, it's probably a picture that looks like this. Right? So I'm guessing that x equals 1 is probably this spot right there. It should be the only spot where this graph is flattened out for a second, a max or a min. How are we going to find the coordinates? Because it says, it didn't say, sometimes it says, like, find the values of x where this is true. Okay, cool, x equals 1, we're done. Yeah.
You plug in the 1 in for x and then solve for y.
Into what?
The derivative.
Well, if we plug it in, we plug 1 into the top. Let's see. Let's see what that does. So you want to drop 1 in up here. So 0, right? So we get 0 over y plus 2 equals 0. Any y makes that true except for -2. And so I don't know if that's going to get us exactly where we want to go. It just kind of confirms what we just found. We just kind of checked it there. I want to figure out what points on this graph make this true. I know it's 1 comma something, and there's probably 2 of them. I don't know for sure, but that's my feeling. It's probably that, and then that, something. 1 comma something. What do you think? Yeah. Yeah, this is the relationship between x and y on this graph. Let's change all of our x's to 1 and see what we get. And I'm gonna, if you don't mind, I'm just gonna do it right away. I'm gonna drop 1 in right there, 1 in right there. So 4 plus y squared minus 8, right, times 1, right? Plus 4y plus 4 equals 0. It's a 0 over there, ran out of space. Right? Every x just turns into a 1. And what this does, at least, is it gives us a chance. Let's simplify it. Let's see, y squared plus 4y. 4 minus 8 plus 4, 0. Nice. Let's get to there. How do we solve that? Well, so you got different powers of y, so I don't want to separate them and try to solve, because eventually I might divide away an answer. Factor, yeah, let's factor. And if there was like a plus 6 or something at the end here, we'd have to do our little quadratic factoring, but this has y in common. So we can just pull that out, and there we go. Set them set them both equal to 0. 0 and -4. 1, 0, and 1, -4. 2. And that's the kind of stuff that they're going to get us going into once we actually like sit down and kind of focus on the applications of this kind of stuff. And you can see that in the coming pages, like right after these, you'll start to see that they even prep us with some AP Calc FRQs. That if you look at just the very next page or 2 or 3, you can see that they kind of get us going on. Okay. And so the only thing that I think would be just worthwhile, just to make sure that your implicit skills are good enough, is to actually turn to this next page and let's just find the derivative. We can save like the part B and part C. So go to 254, because this has this little product rule just to make sure we got that going. Okay. Part A, show that dy dx equals this. Okay, that's okay. Find the derivative. Let's make sure it looks good. Okay. Then it would, find all the points with the tangent line at all your x equal 1s, and find the vertical tangent line. So we just make the derivative denominator 0 in order to do that. So go ahead, try that one, and then I'll show you what's coming. So bottom of 254. There's your equation. We're just going to do part A. Show that that is your derivative. I'm going to use all of this space down here. See if you can do it. Keeping an eye on where you need your dy dx's. So we've got d dx of the left side, xy squared minus x cubed y, and then d dx of the right. And you can go as slowly or as quickly as you're comfortable. I'm going to show one more step with the d dx still in there where I break this left side apart. And of course, that's just going to be 0. Okay, keep the negative inside if you want and just call it plus, or pull that negative out, because it's really a -1, right? That's your constant. The derivative of a function or any relation that has a constant, you pull that constant out. And that's kind of all we're doing. Product rule in here, u and v. Product rule in here, u and v. Side work if you want it, otherwise go for it. I'm just going to say it in my head as I go. U dv. plus v du. There's my first derivative. Make sure you got that before you try this next one, and make sure that that next one all takes place inside a set of parentheses, because we are subtracting the whole derivative, which is going to end up using the product. Take a step to clean it up. Not a bad idea. See any like terms? Usually not, but sometimes we get lucky. Like terms, cover up your coefficient, see if everything's exactly the same. I don't have anything exactly the same. Nothing I can put together, so time to start solving for dy dx. Yeah, sure. Ooh, that looks good. I love when they tell us what the answer is supposed to be, so we can make sure we get there. These are some of my favorite FRQs because they kind of set us up. And even if you like turn the page to 255 to do it again, show that dy dx equals this. So even if you mess it up and you can't get there, you can at least use it for B and C, which is awesome. And of course, these are AB questions because this is a Calc A topic. Implicit differentiation is definitely a Calc A thing. 1 through 4 is Calc A, 5 through 9 is Calc B, and then 10, well, actually, like 5 through 8, I guess. 5 through 8 is Calc B, and then 9 through 12 is Calc C. We try to do about 4 chapters each semester. Sweet. Love it. Man, all of them, 256, 257, they're all very similar. Show this dy dx is true. Find either a horizontal tangent, so just like we did, we'll set the derivative equal to 0, which is really just setting the top equal to 0. Find a vertical tangent, which would be setting the bottom equal to 0. And then just drive it, plug it back in and solve it. So if you know x, you can figure out y. Or vice versa. Cool? Got it? Doing all right? Questions before we use implicit to do probably the most important thing in chapter 4, at least something that Lynch wanted to make sure I got to for those of us heading to BC. Anybody taking AB next year, you'll see it again, so this will be good. But I think we can spend the rest of the week working on related rates and even kind of starting. So go ahead and turn to 258, which is related rates. And then most of next week, looking at the last idea of the semester, which is, my goodness, that's so crazy to say. We'll get into some second derivative stuff. Maybe we'll get into some position, velocity, acceleration kind of conversations with that second derivative, so that'll be nice. But first, we have to take a look at this idea right here, okay? Top of 258. Let's skip. There we go. Yes?
Is there gonna be a test on this chapter?
That is your final.
Okay.
Your final exam, which is not going to be weighted any more than it normally would if it was just a test. Our final exam is a chapter 4 test. So it'll be implicit, it'll be related rates, which we're going to do now, and it's going to be second derivative stuff once we get there. Yeah. Which is why I want to leave, if I can, at least like Monday, Tuesday to review, but I might even stop before that and give us Friday as well, depending on how far into it we get. So we've got like a week and a half at the most to do whatever we can to get ourselves ready. Okay, so related rates. Here's a big part of what makes calculus worth doing is we can watch things happen. We can watch things change, and we can stop a moment in time and figure out how are things changing right here, right now. But in 2 or 3 dimensions, we can have 2 or 3 dimensions changing at the same time. A great example is to think about a ball being inflated, right? The volume of the air inside is increasing. And the radius of the sphere is also increasing. But that's going to happen at different rates, right? Because one is volume and one is linear, right? Also, the surface area of the ball is also changing. That's the second dimension, right? So first dimension stuff can happen with the radius, second dimension stuff can happen with the surface area, third dimension can happen with the volume. And the rate at which, let's say, the volume is changing, of course, makes a really big difference in how fast the radius is and how fast the surface area is. And vice versa, right? If I decide how fast I want the radius to change, I can figure out how quickly something else is changing while I do that. And what you'll see with related rates is that we're going to have some kind of equation, usually some sort of geometric formula, area, volume, trig stuff, whatever, where there are more than one potential spots for things to be changing, right? When you think about the volume of a sphere, for example, the second one was always a good example, right? The volume can be changing and so can the radius at the same time. And it could be increasing or it could be decreasing depending on which way we decide to do. Are we blowing the balloon up or are we letting it shrink down, right? Letting the air out. But the question that we want to kind of consider is, you know, if the volume changes either quickly or slowly, depending on, you know, how fast I let the air out, for example. Same thing with the radius. The radius is going to, like the rate at which the radius changes is going to be different depending on how fast or how slow I want to let the air in or out. So those are dependent, right? Both volume and radius are dependent variables in that spot. And they depend on one thing and one thing only. An independent variable that we have no control over. Right? Because when we think about taking dy dx, the derivative of y with respect to x, it was always with respect to some independent variable, something we didn't really have much control over. And so think about that, like close your eyes and envision this like balloon shaped exactly like a sphere, and the air is being let out. And we get to control how fast it's happening, right? We're squishing the balloon down. We're doing it ourselves. What part of that scenario do we have no control over? Are we controlling the volume? Yeah, we're squishing it down, right? That's on us. As a result of that, are we controlling how fast the radius is shrinking? Absolutely. So the independent variable is not in this equation, right? V is a dependent variable, 4/3 is a constant, pi is a constant, r is a dependent variable. What is the one thing that we can keep track of during that experience? Like imagine me sitting here with a balloon and I was just, right, squish it down. What is the thing that we can use to track? Like how quickly or how slowly that's happening? So the derivative is definitely going to be a rate of change for us, right? And when we look at like the derivative of volume, it's going to tell us how fast the volume is changing. The derivative of the radius, that's going to tell us how fast the radius is changing. But think about that, how fast something is changing. A rate of change. What is the metric that we use to decide how fast or how slow something is changing? Time. That's what makes things go fast or slow, is how quickly I'm changing the radius with respect to time. How fast the radius is changing, the volume's changing, the area is changing, whatever, only with respect to time. When we talk about speed, miles per hour, meters per second, right? Rates of change are always with respect to time, okay? And so what we're going to do when we differentiate is we're not going to do dy dx. We're not going to do ddx of both sides. We are always, in related rates, going to do d dt. The derivative of whatever it is with respect to time. Let's try it. Okay? Let's take this first one. I'm going to blow it up a little bit so I got some more space. And let's see if we can implicitly differentiate this area formula, the surface area formula for a sphere, 4 pi r squared, with respect to time. Let's do d dt. That's a t. My suggestion for your t's, I'm going to draw it bigger. Put a little tail on the end so it doesn't look like a plus sign. Okay, we're going to do d dt of the left side, which is just a. We'll do d dt of the right side, 4 pi r squared. And let's see what we get. Because what I want to be able to do is find a way to describe how fast the area is changing if I mess with the radius. Or how fast the radius is changing if I mess with the area. If I have one rate, can I find a related rate? There we go. Okay, so what does that left side look like? ddt of a. Do the variables match? No, t and a, right? I got a for area and t for time. Those don't match up. And so I would take the derivative as if I normally would, which if it was like d dt of t, it would just be 1, right? Linear, 1. Sweet, there's my coefficient. But I need something attached to that. I'm implicitly differentiating, and the variables don't match. So what do I need?
A DADT.
I need a DADT to go with it, just like I always needed a dy dx when they didn't match. And because it's 1 times, all I really have left is DADT. And what do you think that right there represents? What about the area? Sorry. The rate of change. It's a derivative. Sure, the slope of the tangent line of the function. No, it's the rate of change for area with respect to time. And that's what we're going to write down here in a second. Let's finish up the right side, and then we'll kind of mention, all right, here's what dAdt represents. Let's see what else we get. So the derivative with respect to time of 4 pi r squared. Well, 4 is a constant, pi is a constant. So nothing about that is going to change. We can kind of just hold on to those as we go, right? The derivative of a constant times something is just the constant times whatever the derivative is of the thing that can change. The only variable here on the right side is r squared. So thankfully, we don't need like product rule or anything like that in order to find this derivative. Let's find d dt of r squared. What do the variables match? No, it's r and t. They're different. So I'll definitely need a little implicit little differential at the end there. But treat r squared like you would x squared and you're doing d dx. What would the derivative of r squared be if the variables did match? 2r. But because the variables don't match, we have to attach a factor of something after. What is that? dr dt. And so basically what we've got is this right here, the dA dt, the rate at which the area changes, the surface area with respect to time on a sphere, is 8 pi r dr dt. If I want to know how fast the area is changing, I need to know what the radius is exactly at the moment where you pause time. If I'm going to blow this sphere up, or I'm going to shrink it down. If I want to know how fast the area is changing, I need to know a couple things. I have to know what the radius is at that moment where you pause time, but I also have to know how fast the radius is changing. And vice versa. If I want to know how fast the radius is changing, I need to know what the radius is at that moment in time. So like this is pause time, tell me what the radius is. This is how fast the radius is changing. This is how fast the area is changing. Okay, so let's come over here for a second and let's write those down so we have something to look back at. dA dt is the rate of change for surface area. I'm just putting SA. It's right here. Okay, surface area. It is how fast the area is changing with respect to time. And I want things to match. Like you're going to give me a dr dt and it's going to be in, let's say, feet per second. Well, then my area rate had better be also with regard to feet as its size and seconds as its measurement of time. And depending on what dimension you're in, that'll change what your rate represents. dr dt is linear because that's a radius. So that's feet per second. dA dt is area. It's second dimension. That'd be feet squared or square feet per second. So dA dt, rate of change from surface area, dr dt, okay, your rate of change for the radius. Okay. If it's got a differential like that, dA dt, dr dt, dv dt, dH dt, whatever it is we're trying to look at, it's always with respect to time. The time things have to match up, seconds, seconds, and seconds, and seconds, or minutes, or hours, or days, or years, or whatever we're doing. And the size that we're going to use depends on the dimension. Radius is one-dimensional, area is two-dimensional, volume is three-dimensional. So feet versus square feet versus cubic feet. Okay? Centimeters versus square centimeters versus cubic centimeters. That kind of thing. Okay? And that's kind of the process. Let's do one more at least, just to make sure we've got it. I'd love to actually do some. Maybe we'll come down and do 4 as well. But let's try number 2. Let's implicitly differentiate, because that's always the volume of the sphere. 4/3 pi r cubed. Anything that's round like that always has a constant of 4/3. Anything that ends in a point, like a pyramid or a cone, will always have a 1/3 constant in front. But let's differentiate. Let's take the derivative with respect to time of the left side. And let's do the same thing on the right. Let's do ddt of 4/3 pi r cubed. Now, you don't have to have these geometric formulas memorized. You do not need to know surface area of a sphere, volume of a sphere, surface area of a cone, volume of a cone, area of a pentagon. You don't have to know those kind of things. Those will be given to us, which is nice. And here they are. You can always look back at them. But you do want to figure out how many variables you have, because sometimes, like in these cases, the only thing that matters was radius, because it's three-dimensional. So sometimes we could have length, width, and height. But because it's round like this, the only thing that matters is the radius. So that makes finding the derivative a little bit easier. Okay, so what do you think? Left side, d dt of v. dv dt. The derivative of volume with respect to time, the rate of change for the volume. How fast is the volume changing? Cubic centimeters, cubic yards, whatever, depending on what we're looking at.
Cubic kilometers.
Sure, let's get crazy, right? Why not? Right, you could talk about the volume of the Earth. It's not exactly spherical. If it stopped spinning, maybe it would be. But I think at this point, I think we're kind of stuck spinning, which is good. You know how fast we're moving right now? Just like rotating around. Let's say we're on the equator. You know how fast it is? Take a guess. How many miles per hour do you think we're moving right now if we were sitting on the equator, which is going the fastest? 300 what, miles per hour? Well, 1,000 miles an hour. Over 1,000 miles an hour. It's like 1,100, something like that. That's how fast we're moving right now. But that's just in a circle. We're also whipping around the sun. And we're going even faster that way. But our solar system is moving through the galaxy at an even faster rate. Our galaxy is moving through the universe at an even faster rate. And our universe is expanding even faster than that. So cool. All right, right-hand side here. I can talk about this all day. 4/3 pi, all constants. Nothing I have to worry about right there. 4/3 pi. Times, okay, now let's really focus in on the variable itself, r cubed. Find the derivative with that, but with respect to time. Treat it like you normally would, and because the variables don't match, we'll just have a differential attached. There it is. 3r squared, right? Drop the exponent in front, keep the r the same, decrease the power by 1, and then multiply by the derivative of the inside, like a little chain rule kind of action there. Now let's clean it up, make it look nice. dv dt equals, all right, what do you see? Do you see anything we can get rid of? Right, the 3's, 4/3 and times 3, so those are gone. Constants up front, 4 pi, r squared dr dt. Voila. There it is. And that's always true, just like this is always true. The derivative of volume is always going to be, for volume of sphere, 4 pi r squared dr dt. Do you notice something about that derivative, though? Does that look familiar at all? 4 pi r squared dr dt? Huh? It's got a pi in it, which is always going to be the case when we have like circles and stuff. This is just a three-dimensional version. Look at the derivative. Look at dv dt. 4 pi r squared dr dt. Look, right here, look at number 1. The derivative of volume is area times just the rate of change with the radius. What dimension was volume, by the way? What's the third dimension, right? We're talking about volume, right? Cubic centimeters or even like liters and stuff is really, it's a third dimensional kind of thing. What do we do with derivatives? Like I take the derivative, what happens to the degree of something? It goes down by 1. So we go from third dimension down to second dimension. What kind of measurements is a second dimension? Area. The second dimensional measurement. Crazy. Like I can even like anticipate what it's going to be. The rate of change for volume is area. A formula from area. It's just crazy that it works out that way. Okay, but it's really just dropping it down. Okay, so again, let's mention what we've got here, what these rates actually represent. What do you think you call dv dt? What is that? Describe it. Yeah.
Rate of change for the volume of sphere.
There it is. Rate of change for volume of a sphere. Now, we've got other volume formulas. I've got volume of a cylinder. I've got volume of a cone. Those will have different types of dv/dt's depending on what we're looking at. But hopefully they'll relate nicely back to whatever shape makes that, right? Volume of a sphere, we went back to surface area, the area of that. If I wanted volume of a cone, and I wanted to find dV dt, it would be the area of the shape that made that cone, right? Things like that. And then dr dt. What's that?
Rate change for the.
Rate change for the radius. Voila, dr dt. How quickly the radius is changing as we go. And if we can do this, if we can find the derivative of both sides of whatever equation's given to us, then we can use related rates to look at something happening, watch something take place, but then pause time, look at a dimension that we can measure, figure out a rate that we know, and use that to find another rate that we don't know. And that's the thing about what's here, like dV dt, r and dr dt, there's three missing pieces to this. Two rates and an actual measurement. If you want me to solve for one of them, you better give me the other two, right? I can only have one missing piece within one equation, so I better have something that I can use to find that missing piece, okay? Now, we could do the derivative right there. We could do the derivative right there. Let's look just for a second. I guess because we're running a little short on time, maybe we'll actually do some related rates tomorrow. Let's just do one more here. Let's do number 4. Because every time we'll do it, we'll find the derivative as we go. But let's find ddt of both sides. Pi r squared h. Volume of a cylinder is a little bit different than volume of a sphere, because I can change a couple different things about a cylinder. I can change how big its base is, right? It's got a circular base if they don't say otherwise. Circular base, I can mess with the radius of that circle, but I can also mess with the height of whatever the cylinder is. Left side's easy. What's ddt of v? Left side? dV dt. The derivative of volume with respect to time, the rate of change for the volume of this cylinder. Now again, we've got a constant here, so I can pull that out. That pi will just kind of be part of everything. I mean, you can like make that part of your derivative process, or you can just pull it out and make your life a little bit easier. Totally up to you. Now let's find the derivative of what's left. And what's left is that stuff right there. How many variables do you see inside those blue parentheses that is true? And what's happening to them? R squared and h, how are they connected? So what are we going to need to use to find the derivative of a product? Product rule. U is r squared, and v will be h. So here we go. So I pulled the pi out, so I didn't have to worry too much about it. You can call like your u could be pi r squared, that's fine, and your h would be v. Question or answer?
Question.
Question.
It says the radius is a constant. So
Oh, look at
just
that.
pull out R.
We could. Look at that. They're telling us that the radius is not going to change. You're right. It is a constant. This is huge. That makes such a big difference to the process that we need in order to find this volume. But what if it wasn't? Right? What if things could change? If things could change, we would need the product rule because R is changing potentially. In this case, it's not. Let's just do it where it could be changing, and let's talk about how it's going to affect the rate of change as we go. So let's just do it anyway. So pi r squared h, so here it comes. U dv, so that's dh dt, plus v times du. The derivative of r squared to r dr dt. Which, if we multiplied things back together, pi r squared dh dt plus 2 pi r h or hr. I guess hr is better because alphabetical. Either one's cool though. Everyone feels right to you. We'll go hr. We'll go alphabetical. dr dt. That's your dv dt, given a volume of a cylinder that maybe we do have control over lots of things. But in the case where r is a constant, so we're going to mess with the height of this Pringles can, but we're not, you never change how wide it is because what a waste, right? Can't make it too small because the Pringles will be crushed. Can't make it too big or I'm wasting all this space because Pringles are always the same size. I guess I want some Pringles. Good, just can't. I like Pringles. Pizza flavor, so good. If that is the case, if r squared, which is the part of this that would be staying constant, what would this be? The rate of change for the radius if I'm not changing the radius. 0. And all of this would disappear. Okay, but if we could control how big or how small the radius got, that would be the whole. And so sometimes along the way, we're going to need the product rule to find ddt of whatever we're looking at. Maybe we'll need the quotient rule. Maybe we'll need the chain rule. Right? Cosine of theta. I want to find ddt of cosine of theta. Well, my variables don't match. So I would find the derivative of cosine, which is negative sine of theta, but I would need a d theta dt after that. Things like that. Good enough place to end there for me. Tomorrow we will actually do some related rates, which you can see on the very next page. Air is leaking out of an inflated balloon. Stone is dropped into a calm body of water. Water is leaking out of a cylindrical tank at a certain rate. Water is being poured into a cone. A ladder is leaning against the wall of a house. An airplane, sphere, a balloon. There's just so many. These are fun. I like these a lot. We will never do all of these, but there's so many good ones. But we'll spend tomorrow kind of getting used to doing this. And then Friday, as a reminder, I'm not going to be here. Seniors, if you need me to sign your checkout sheet, it needs to be today or tomorrow because I'm not going to be here on Friday. So make sure that we do that. Friday, when I'm not here, I will let you know what I would like you to do in here, and then you guys can, what's up, Jack? And then you guys can just submit that to Canvas for your work for Friday, so I know that we got some stuff done in my absence. And then we'll pick it back up on Monday.
You get that shirt at Target?
Good?
That's
Jack,
what
I'm
mine.
talking, buddy. You didn't mean to interrupt, but you just walk into the middle of my class and say what's up and talk about a guy's shirt? Okay. It is a nice shirt. I like the color. We're good. We are good. We got one more minute, so hang out, and then I will see you tomorrow. And we'll go from there. Thanks, everybody. Uh-oh, what happened here? Some updates could not be installed. I don't want you to.
Yeah. I'm so glad I'm having more. I'm like,
Done? You took your last AP?
yeah.
Nice.
Seriously, like.
What's this morning? AP Lit?
Yeah, I think so. I'm not.
Lang, AP Lang?
Oh, that's
I forget, it's one of the two. I think it's an English one.
I like don't know what to do with
Things
my
like
free time,
lit
because I
sound like
freaking
hell.
hate it.
That's not my cup of tea, that's for sure. Thanks, everybody. Have a good day. See you tomorrow. Yeah, no way. I would never. Thanks, you too.
Intensity. People get
Adios. What's up, Hayden?
Hopping.
I'm good, buddy. How about you? How was your night?
Good.
All good?
Yeah.
Do anything fun?
Yeah. That cross game.
Oh, nice.
That was
Crushing them, right? Let's go, baby. Shut out TR.
cross game. Yep. Shut up. 12-0.
Love it. Love it. We got Evergreen. Today's our first game.
Okay. Yeah. We are. Senior night
What's your
is,
team called again?
Friday with Tyler.
No, us. Mustangs. Yeah.
What's your team called?
My baseball team, the Hops. Denver Hops.
I thought it was Schnapps or something else, that's not right.
No, the Hops.
What's Schnapps? I forgot what Schnapps was. I think it's it's part of it.
It's kind of some kind of league.
That's a good logo though. That's a-
Yeah, I like it. We stole it from, there's a minor league baseball team outside of Portland, Oregon.
How do you guys get away with stealing logos? Like, that's super illegal.
It's not because we changed it. There's a DH for Denver. Denver Hops on the top. So it's not the same.
Rosie, these kids over at I think it's also DH, it's Denver High School or whatever.
Really?
Yeah, they
Is that Denver High School?
Yeah, we wrestled them. They just literally stole the Vikings logo.
Really?
It didn't change anything. I'm just waiting for the Vikings to figure this out.
Well, I don't know if that kind of stuff is really copyrighted because it's more like free use of certain things. I don't know, like, because there's so many teams that have the same names. Like,
Have the Vikings been around for 100 years though? That's the cutoff.
well, in terms of like copyright infringement, like that kind of
It
thing.
becomes after 100 years, it becomes public domain.
Right. I don't know. Probably.
And
Yeah.
Disney is pissed because they lost the rights to Mickey Mouse.
What?
They lost the rights to Mickey Mouse.
Really?
That was on the first episode.
No.
Yes, it was. I was like,
I know, I saw it.
And they're mad. I'm like, yo, that is kind of bullcrap because they're so opposite companies.
And then
Disney
I was like, I'm really with him.
They certainly could. I agree.
They sued
Well, don't
some
be
kids, some
pissed.
rich kids' parents because they put Spider-Man on his grave.
Come on. It's like